slide. We'll just quickly look at what we're covering in today's session. So I'll firstly quickly have an introductory overview of what a blockchain is. Then we will move to the tenets of cybersecurity, as most of you may already know, and we'll see how blockchain fits in this equation. Then we look at why blockchain is deemed to be the next big thing in cybersecurity. We'll look at how it's providing the function of immutability. We look at the security of all the blocks involved in blockchain. We look at the consensus algorithm and the proofs used in various blockchain technologies, various frameworks, and we'll see which consensus algorithm fares better than the other, and why the adoption of one consensus algorithm can be preferred over the other, like in which cases. A consensus algorithm basically is the practice or the state of maintaining the same ledger record of the transactions in the blockchain across all the participating entities. So we'll again cover that in detail later. Then we look at um, an overview of sorts of public versus private blockchain. In which case should you use which? Next, we'll see the working of Hyperledger Fabric, which is a very popular example of private blockchain, and we'll see why it's used so widely uh, in improving business processes, particularly. Then we look at how blockchain is becoming widespread and how various cloud platforms are providing blockchain solutions through blockchain as a service. And well, no technology can be 100% foolproof, especially if it's emerging. So there are a lot of inherent vulnerabilities also in blockchain. So we look at those so that we can be better prepared at safeguarding our networks against them. And lastly, if we have the time, we will see a use case of blockchain, of how you can implement blockchain to solve existing problems that we see, status quo. So if you can move on. Yeah. So the principles of blockchain, um, the reason why it's so important to know this is because we know of the traditional cloud server architecture. Sorry, client server architecture. We know that a server has various clients, and um, that has always been the traditional way we have looked at the internet. But the reason why proponents of secure internet practices are against this architecture is because of the obvious reason. There exists a single point of vulnerability, the single point of vulnerability being the server itself. So if a hacker is able to successfully attack a server, it can pretty much put the entire network in jeopardy. It can leak potentially sensitive data, confidential information of the network that was supposed to be protected at all cost. It can compromise the security of individual clients as well, and it can lead to massive data breach. That is something that we are observing these days, because we can see that the businesses are moving online. Even the education business is moving online, as this lecture itself um, can epitomize that. But as we're going digital, the cybersecurity practices are not evolving with the widespread adoption uh, of going online or of being on the internet. So um, that's why these days we're noticing a lot of data breaches, and that led to the whole questioning of the traditional client server architecture that we have employed. That is very centralized. So we see this transition from a centralized computing, storage, and processing system to a decentralized architecture and system. So blockchain is obviously not the first decentralized system, but is certainly probably one of the most popular ones. And the reason why it's the most popular ones is because apart from providing decentralization, it provides an immutable history of transactional records. Well, if I were to simply define blockchain, I would say that it's a database. It's a database that's, only read only, because you cannot really make any changes to the database. And it's a permanent record of each and every transaction that's ever happened on the network. And every single participant always has access to it, which is again why authenticity is maintained, because we can ensure who has access to how much information in the network. And because of the immutability factor of blockchain, the records are permanently linked to the system, which makes it tamper proof. And the peer-to-peer network again ensures that the entire information is distributed equally amongst all the participating nodes. This proves that the technology is very powerful and validating. Blockchain is actually often confused with distributed ledger, but I would like to point out that blockchain is actually only a subset of distributed ledger, which also has smart contracts and consensus. So, a distributed ledger is actually a data structure that resides across multiple computer devices, across all the participating nodes, or all the participants, or all the stakeholders of the network, of the blockchain network. Now, distributed ledger technology is basically blockchain with smart contracts. Smart contracts is a program code where I define a logic uh, through which I can decide if the transaction that I'm getting from a participant is valid or not. So let's take a simple example. If suppose I have $20 in my account and I want to transfer $10 to somebody, that's sound business logic, because the amount that I want to transfer should be equal to or less than the amount in my account. So as long as my transaction is satisfying this business logic, it's a valid transaction, and it can be embedded in the blockchain. So when a number of valid transactions, when they're grouped together, they form a block, and each of those blocks are independently then committed to the blockchain. Again, we'll cover that later, but that is how the flow is. Consensus, as we've previously seen, is the practice of maintaining the same ledger values, the same transaction records across all the participants of the network. And yeah, a few other terminologies that are needed for distributed ledger technologies is the data model, which captures the current state of the ledger. There is a language of transactions, which changes the ledger state. There is protocol to build a consensus, which helps sync data on the blockchain network and ensures that all the participants are accepting the same transactions in the network. So, to summarize all of this, a blockchain is a peer to peer distributed ledger that is forged by consensus and combined with smart contracts through which you can prove if your transactions are valid or not. So, that in a way epitomizes trust, accountability, and transparency across the entire network. If we can move on, sir. So, this is the uh, there's
Sorry. Yeah.
yeah. So this is the layer. These are the layers of blockchain. So if you can draw a rough analogy, it's very similar to the TCP suite. At the top, you have the application layer through which clients can interact with the network, um, and can send in transactions. And later on, the blockchain will check if the transaction is valid or not. In the smart contracts layer, you check the logic of the transaction, if the transaction is valid or not. The incentive layer is again something that is very um, inherent to to permissionless blockchain. It's something that we'll cover later. But to give you an example, Bitcoins and Ethereum blockchain. So they use this incentive layer actually quite liberally because to establish security, the network is completely dependent on the nodes. Nodes are basically the miners of the network. So, Bitcoin is based on the great hash power that many nodes participate in, which makes it impossible for attackers to provide a higher amount of computation, which makes the system overall more secure. But since the nodes are spending their own computational resources in order to make the system more secure, the blockchain network, provides a virtual currency of sorts, as in an incentive to encourage the nodes to participate in the security verification of the blockchain. Next, we have the consensus layer, through which, like I said, we maintain the state of the blockchain across all the participants. We have different consensus algorithms that we'll, I think, cover in the next slide. And the next layer is network layer. So this is the basic framework of blockchain. It's the basic peer-to-peer architecture of every single blockchain. So it basically deems how the information can travel only across peers, and there's no single, centralization as such. And lastly, we have the data layer, which governs the signatures and the encryption method and all the cryptography bit of cybersecurity, where we define which cryptographic algorithms to use, which hashes to use, whether to use MD5 or SHA-1 or SHA-256 or SHA-512, whatever. Right. Moving on. So, as you all may already know, these are the three tenets of cybersecurity: confidentiality, integrity, and availability. Now, let's look at how these basic principles of cybersecurity can be very efficiently satisfied by blockchain technology. So, as NIST would define it, confidentiality is the property that sensitive information is not disclosed to unauthorized individuals, entities, or processes. It's basically the practice of including authentication and authorization in the system. So the reason why blockchain fares well in this category is because it addresses the access control challenges that networks face. So there is full encryption of the blockchain data always on the network. So even if you somehow send this data to unauthorized users, or if somebody manages to snoop this data through a successful man in the middle attack, or if the data does flow through unsecured channels, the data in itself will be safe because there is encryption in place. Next, the network access is also restricted, or can be restricted, at least in private blockchains or permission blockchains. We'll again get to what is permission blockchain, what is private blockchain, and public blockchain. Just at the stage, know that network access can be restricted. So every single blockchain is not public. Every single blockchain is not accessible to every random person on the internet. So control over who enters the network, who has how much access to the network, who has read write access, all of that can be controlled in a private blockchain and in some extensions of Ethereum. Sessions can also be kept private with private key and encryption. And even if the key happens to be compromised, the previous session is kept confidential. So that is actually a fantastic feature of blockchain. And even in a successful man in the middle attack, the identity of the compromised participant cannot be forged. Next important tenet, no, so if you can go back, is the integrity feature of cybersecurity. So that's essentially guarding against improper information modification or destruction, and includes ensuring information non-repudiation and authenticity. So again, the reason why blockchain fares well here is because of its immutability feature and its traceability feature, which ensures data integrity. So there is sequence hashing in place, there is cryptography, there is decentralization, which makes blockchain more secure than a traditional database. And every transaction is digitally signed by the participant that has a made the transaction and also who has admitted the transaction in the blockchain. So there is 100% traceability as well. And the next tenet being availability. It basically deals with ensuring timely and reliable and access to and use of information. So again, the reason why blockchain fares well here is um, well, mainly because of its peer-to-peer decentralized system. So you guys might probably know about a denial of service attack, right? Wherein you flood the server with a lot of requests, which basically crashes the server in simple terms. So the reason why the likelihood of that is less in blockchain is because of the peer-to-peer network. The denial of service as such cannot happen because that entire risk is distributed across all the peers in the network. So the overflow of network with request is rarely a possibility in blockchain, and there's no single point of failure because of the network being peer to peer. So there is 100% resiliency. As long as there is even a single peer functioning up and running in the network will function, will run. And there is operational resilience again because the network is distributed. Right, so if we can move to the next slide. uh, right, so this is about security of blocks and immutability. So the very first block in the blockchain is called the genesis block, and a sequence of hashes link each other to each block to uh, its parent that creates a chain going all the way back to the genesis block. So each and every block, when it references the previous block, which references the previous block, which references the previous block, you reach the genesis block. So the reason why this is an important feature is because if the parent block at any step of the blockchain is modified, the parent hash also changes, which changes the previous block hash of the child. Because if the parent hash changes, the uh, obviously the previous block hash of the child will also change, which changes the grandchild previous block hash, which changes the next block, which changes the next block. So if a malicious user wants to modify an entry, he will have to do a lot of recalculation, because he'll have to recalculate all the hashes of all the blocks, which requires enormous computation, which is practically impossible, at least in the current setup. So if we see how immutability is practiced here, um, you see that each and every transaction is hashed, and then it forms a metadata in the block. Now, every single block carries two things. It carries a body wherein all the transactions are grouped, which forms the body, and it carries a metadata. Now, the metadata are those four boxes that you see. It's a reference of the previous block through the previous hash field. There is a timestamp, which again cannot be put by a user. It has to be put by a blockchain, by the blockchain. There is nonce, which is actually proof of work. It's a type of consensus algorithm that we'll discuss later. And the general Merkle tree root. So the Merkle tree root is can also be referred to as a binary hash tree, which is essentially a data structure that is used to store hashes. It is completely tamper proof, and as you can see, they summarize all the transactions in the block, producing an overall digital fingerprint of the entire set of transactions in the entire network. So, how is this immutable per se? So, if you look at transaction A, if I make any modification in transaction A, transaction the hash associated with that transaction A will also change, which will change hash AB, which will change hash ABCD. So that will essentially change the hash of the entire block 11. But that hash is referenced in block 12 as previous hash. So that hash also changes. Then I have to recompute and change block 13 also, because that hash will also change, and so on and so forth. So this is how immutability is established in blockchain, because you cannot modify even a single transaction because the entire hash will change, which will change the entire blockchain, and it's not possible to change the entire blockchain. Right. So moving on. Right. So here we discuss the consensus algorithms and proofs that are used in blockchain, various blockchain frameworks. So the very first is proof of work. So, um, well, in layman's term, it's basically mining. So the nodes here, in this case, as we would call them, are called miners, who solve a computational challenge, which is a cryptographic hash for an economic payoff or an economic benefit or an incentive, as we had discussed previously in the layers of blockchain, if you remember. So here you have to solve a computational hash, and that helps you mine the next block. And the motivation behind it is economic payoff. But there are a few criticisms associated with this consensus algorithm. The most popular one being 51% attack. So if you know how a basic Bitcoin or Ethereum network works, it's essentially that if any miner pool owns more than 50% of the total stake in the network, they can deem if any transaction is valid or not. And it's very easy for a mining pool to become malicious. So even if a transaction is legitimate, the mining pool that controls the major stake in the network, if its intentions are not correct or legitimate, it can even discard honest transactions. So that's a heavy criticism proof of work consensus algorithm faces. And of course, it's heavy on computational resources. As you know, we can't decode these hashes on our normal PCs. You need dedicated servers for that. And because a lot of computational resources are required and it takes a lot of time, there is inherent latency in the network. So this is not a very useful algorithm when you know that you're going to be transacting with the known set of participants always. But this is great if you want to perform transactions with unknown people all over the internet without revealing your identity. So the next algorithm is proof of stake. So here you're not really mining anything, but there are validators here. So it's actually a generalization of proof of work. So instead of mining, they validate transactions, as in they see if the business logic of the transaction is valid or not. And for that, they earn a fee. So the nodes here, the participants here, instead of being called miners, they're called validators. And the choice of validators is also made depending on the amount of stake they have. So if, for example, I have 2 units, and if somebody else has 1 unit, then I get precedence over that other person in being a validator. That again faces a lot of criticism, because it's very easy for centralization, or the 51% sort of attack that we see in proof of work happening, to happen here as well. Because um, if I have more stake, I have a higher likelihood of deciding which block will get admitted in the blockchain next. So In a way, it always favors the more dominant mining pool. Well, not mining pool in this case, the validator pool. Um, Next is proof of elapsed time algorithm. So this is something that we see in Hyperledger Sawtooth. Here, again, it's an improvised version of proof of stake, and every validator gets a random wait time. It's actually a hybrid of a lottery system, a random lottery, and a first come, first serve basis arrangement. So, what happens is each validator gets a random wait time, and the one with the shortest wait time gets elected the leader and gets to create the next block. So, in simplified Byzantine fault algorithm, which is the next algorithm, it's an improvised version of the simple Byzantine fault algorithm. So here again we have validators. The only difference is here validators are predetermined, they are predefined, and they are permissioned. They are known parties, they're known entities, and they bundle transactions and form blocks of valid transactions, and they commit the blocks to the blockchain. And this consensus can be maintained, as in the same ledger state across all the peers can be maintained if we have 2f plus 1 nodes to do this validation bit, where 3f plus 1 are total nodes and f are faulty nodes. So for example, if there are two faulty nodes in the network, we need 2 into 2 plus 1, that is 5 nodes to reach consensus, and where there are 3 into 2 plus 1, that is 7 total nodes in the network. And lastly, we have proof of authority. It is a very popular consensus algorithm in permissioned blockchains and permissioned ledgers, where a set authority is given the task of designing, of creating blocks, of admitting blocks. There are designated roles. That's again something that we'll see in the working of Hyperledger Fabric when we get there. Yeah, and so let's move to the next slide. Right. So this is a basic distinction between a public and a private blockchain. So there are a lot of similarities between public and private blockchain. Let's address that first. Now both are blockchains, so they are decentralized peer-to-peer networks at their core, where each participant maintains a replica of a shared append only ledger, not edit only, append only ledger of digitally signed transactions. And both maintain the replicas in sync through a protocol referred to as consensus, as we have discussed till now. Also, they maintain the principle of immutability to ensure that records cannot be forged in the network. But the basic distinction between public and private is that a public blockchain can be viewed as to draw an analogy, it can be viewed as being all of internet, whereas a private blockchain will be only intranet pages that can be accessed only within an application, within an organization. So, to elaborate, a public blockchain is open. There is no privacy, which basically means that, to quote an example, if you look at Bitcoins or Ethereum, there, as long as you're able to solve the hash, you can enter the network. So, it's open to all. There is no privacy because anybody can enter. Whereas private, on the other hand, can be accessed by invitation only. Next major difference that we see in public and private is that public uses the proof of work consensus algorithm for proving the identity. Like every participant has to solve a hash to prove their identity, and that takes up large resources. Whereas in a private blockchain, the identity is pre-validated, so you don't really have to solve huge hashes, and you don't really have to waste your organization's resources. And yeah, well, the next major difference is that a public blockchain is permissionless, which means that as long as you're able to solve the hash, you can enter the system. So a public blockchain can also be loosely called as a permissionless blockchain, and a private blockchain is permissioned. You need the network administrator's permission to view the data of the blockchain, to make commits to the blockchain, or to just be a part of the network. And lastly, because it consumes huge resources, the public blockchain is not really scalable, but private blockchain is, it does have a lot of scope for scalability, and its transactional throughput is a lot. So if I roughly compare the number of transactions performed in Hyperledger Fabric, which is a popular example of permissioned blockchain, with a permissionless blockchain such as Ethereum or Bitcoin, I can perform approximately 100 times more transactions in a minute that I can through Fabric than I can through Ethereum or Bitcoin, which is why private blockchain networks are seeing a lot of adoption in the business sphere, wherein you know that you're always going to be interacting or transacting with known parties. You know that you're always going to engage with a certain set of stakeholders. For example, your manager, your client, your partner. That these stakeholders will always be involved in most of your transactions. So it's illogical to ask them to solve a hash each and every time you want them to prove their identity. It's just unnecessary wastage of resources. That's why we observe Hyperledger Fabric being adopted very widely in businesses, in ensuring safe cybersecurity practices are implemented in businesses through Hyperledger Fabric blockchain. Again, we'll get to that later. But yeah, let's move on to the next slide for now. Right. So let's cover quickly the working of Hyperledger Fabric. So it's distributed architecture of distributed logic processing and an agreement, which is called a chain code in this case. A chain code is basically, smart contract. It's just called chain code in this case. There is transaction ordering, there is transaction validation, there is commitment, there is increased confidentiality, there is resilience, and there's flexibility. Um, and it is permissionless. It is permissionless. So sorry, it is permissioned. So it can be widely adopted across all businesses. So these are the databases options available in Hyperledger Fabric. There is CouchDB or LevelDB. Um, and the choice of which database you want to use out of these two is made when you're configuring the peers are the participants in the network. So like in the case of bitcoins, we call them nodes. Here we call them peers. And there is a NoSQL database wherein you maintain all the general data of the blockchain. You maintain the keys, and it's used in the backend for data storage. And transactions are encrypted and mapped against a transaction ID and stored here. And to decrypt, the user's private keys needed. Next, we see the working of Hyperledger Fabric. So, the basic flow is the communication between three entities. We have a certificate authority, we have a user and the user's wallet, and we have the client application. It can be SDK or it can be REST API. Completely depends on how the client is interacting with the blockchain. So the user sends a request for acquiring certificates to the certificate issuing authority, and the CA in response may issue a certificate. So the certificate authority sends it to the user's wallet, where the user can use it to sign the transactions, which basically means encrypt transactions, or it can use to verify, that is, decrypt transactions. So what happens here is, through the SDK, the client sends a transaction request to one of the peers. The peers it first sends it to is the endorsing peer. Now, the endorsing peer is responsible for checking if the transaction is valid or not. So it has to have the chain code, that is the smart contract in case of Hyperledger Fabric, wherein it checks the validity of the transaction. So if the transaction is valid, it sends back a send proposal response back to the SDK after checking the logic, and it also sends the original request so that there is complete clarity in terms of what the endorsing peer has interpreted. So, if maybe the request was for some reason modified before reaching the endorsing peer, or if the endorsing peer has not interpreted the request as it should have, when it sends back a copy to the application SDK, the client can check if the request it meant to send to the endorsing peer has been sent, or has been received by the endorsing peer the way it should have been. So it checks if the request was sent properly or was misinterpreted, and if it's right, it sends back a validation to the endorsing peer that yeah, what you've interpreted is correct, and then it submits the transaction. Now the transaction goes to an orderer. The orderer is responsible for grouping transactions into blocks. Now, the consensus algorithm here can be Kafka or Solo, which basically determines how many orderers or ordering services are present in the Hyperledger Fabric network. So, if there's only one ordering service, it's called Solo. If there are multiple ordering services, it's called Kafka. Now, obviously, on a production setup, it is recommended to have multiple orderers so that if there's failure in even one of the orderers, the entire system does not go down. And you're right. So the job of the auditor is to group transactions into blocks. And once that grouping is done, it goes to the committing peer. So now this grouping also is a very crucial step, because if the blocks are huge, and if the transaction, even if one of the transactions in the block proves to be invalid or fatal or malicious, the entire block has to be discarded. So it's very important to determine what size of the block you want in your blockchain, to ensure that even honest, legitimate transactions are not discarded if it's grouped with one malicious transaction. So then these blocks are committed to the committing peer, are sent to the committing peers, who may or may not have the chain code. They don't really need to have the chain code, since the business logic or the smart contract has already been checked by the endorsing peer. So they may or may not have it, but their basic job is to admit the blockchain in the blockchain. Sorry, admit the block in the blockchain. So that is basically how the transaction flows in a blockchain. Next we see um, how these peer-to-peer networks or peer-to-peer uh, and participants in this peer-to-peer network are maintained isolated. So the heart of Hyperledger Fabric is Docker containers. So as many of you may know, Docker is widely used by cloud services and cloud platforms these days to provide the feature of containerization of applications, of softwares, of systems. So the reason why the industry is a proponent of containerization, if you've heard of Dockers and Kubernetes, is because they want systems and entities that can function on their own to be isolated from the others. Now, the motivation behind doing this is because even if one of the systems fails, the entire system does not go. Even if one of the participants or one of the entities, if they fail, the entire system will not go down. Only that container will crash. So if you can see here, um, peer 0 of org 2 of example.com has one orderer, and sorry, has one Docker container which has a container ID. Then an orderer has a separate container ID. It has a separate Docker container. Then all the different peers, peer 1 of org 2, peer 1 of org 1, peer 0 of org 1, they all have independent Docker containers, which shows that if you want to have complete isolation, and if you want to keep the network up and running always, you have to ensure that all of these nodes and all of these peers are isolated completely. Okay, moving on. I see we're sort of short of time, so next, we talk about blockchain as a service. So, with the advent of a lot of popular cloud platforms like Azure, Oracle, AWS, and with the advent of infrastructure as a service, or software as a service, platform as a service, blockchain as a service was only inevitable. So, blockchain as a service is hugely responsible in the widespread adoption of blockchain, because um, uh, since it's a new technology, it's uncharted territory. A lot of developers are wary of trying something that they haven't been doing traditionally. So, blockchain as a service allows customers um, to use cloud based solutions to develop, host, and adopt their blockchain applications, smart contracts, and other relevant functions on the blockchain. While the cloud based IT partner like Azure or AWS manages all the required tasks and activities to keep the infrastructure up and running, the logic in itself is defined by the user of the blockchain as a service. So this is an essential milestone in blockchain landscape because it aids in the acceleration and adoption of the distributed ledger technology across businesses. So blockchain as a service is, like we discussed, a third-party cloud-based infrastructure, and it's a tool for management for companies for building and operating powerful blockchain apps. And Azure blockchain solution currently probably only has support for Ethereum blockchain, and AWS blockchain solution has support for both Ethereum, a popular um, public blockchain as we discussed, and Hyperledger Fabric, a very popular um, private blockchain. Okay, moving on. Right. So as we discussed, blockchain is a very powerful tool when it comes to transparency and immutability and decentralization. But there are still a lot of inherent vulnerabilities. So let's try to cover them one by one. These are obviously not all of them, but these are some that I found to be, well, sort of deal breakers if they're not addressed immediately. And if you're looking at as if you're looking at adopting blockchain everywhere. So the biggest concern that we see is the centralization bit that we see in bitcoins or Ethereum. So what happens here is a malicious mining pool um, can control 50% of the total hash power. It can control which transactions are valid or not. So even if a legitimate transaction comes, it can very well discard it. So this is a serious problem because the core of blockchain is supposed to be decentralization. But when there is existence of a mining pool, it violates the principles of decentralization, which controls 50% of the hash power of the entire network and can manipulate the mining rights. It can change the billing rights or the distribution rights of which information is available to whom in the network. Well, next we have the selfish mining attack. This is again something that we see in Ethereum and Bitcoin. So, if a malicious mining pool again decides to not release the block it finds, it can create a fork. Now, if this private fork becomes longer than the public fork, as in all of the Ethereum network, for example, even honest miners will deem the private malicious fork to be the legitimate one, and the right data will be discarded. Now, obviously, for that you need a lot of computational resources, you need a lot of lobbying and such, but it is still a possibility that we cannot rule out. Next severe vulnerability is that identity may um, um, identity may not be anonymous or can become malicious if the network traffic is mapped or if the transaction information is mapped. So your identity can also be compromised. And um, mm, right. And the next point, being well, as we discussed while seeing the layers of blockchain, at the incentive layer, the incentive to provide security to the network depends on the nodes. But um, it may happen that maybe the working cost of the networks, of the nodes, is higher than the income that they're getting from the virtual currency. So they may choose not to work towards creating centralization. They may just choose not to work, which will compromise the overall security of the blockchain, because there will cease to exist one giant hash power. So this again puts a threat on decentralization if the nodes are not motivated enough to contribute always. And while blockchain as a framework is very efficient, if the underlying data layer is not safe, as in if the signatures or the encryption method is not good, if you use poor cryptography, like if you use outdated, obsolete hashing methods like MD5 or SHA, it's sort of easier, relatively easier to break the encryption through brute force or collision or backdoor attack, which does not leave the data, completely secure. And another vulnerability that can occur is if the smart contract is not programmed properly. There can be race conditions, there can be denial of service based on exception rollback. So to give you an example, race condition, for example, the control flow um, can be hijacked, and it can modify the contract data if an error occurs. Denial of service attack again. Let's take an example. For example, we're looking at refunding some contribution amount, maybe to a group of people. And if suppose the logic is not defined properly, such that if one malicious user fails the refund logic on purpose, the rest of the people in the chain will also not be able to get the refund. So it's very important that you define logics that are independent, functions that work independently. So programming a smart contract, again, the onus is completely on the network administrator and designer. So that is again something that cannot be controlled by blockchain, but is an inherent vulnerability if it's not addressed properly. The next issue that we have with blockchain is because it's an emerging tech, there is not enough regulatory guidelines present on how to check if data privacy is maintained, how to check if network conditions are proper. And we have other vulnerability issues, like there can be improper pre-validation of participants. This is a huge problem in permission blockchains like Fabric, wherein you're not making the participants or the prospective participants solve a hash. You're predetermining their identity and then admitting them in the blockchain. So what if their identity before being admitted in the blockchain is not verified completely? You can potentially give access to your crucial information to malicious users as well. And another issue that we've not covered here is a compromised database. So as you saw, all of this information in Hyperledger Fabric, for example, is stored in a database, either CouchDB or LevelDB or NoSQL wherein each transaction, although encrypted, is mapped with a transaction ID. If the database is also compromised, without actually exploiting any vulnerability in the blockchain, if I just work at exploiting the database, I can still get all of the data without even touching the blockchain. So these are some concerns that industry leaders should look at if they want to adopt blockchain more widely. Next, right. So if we have the time, sir, do we have the time? Um, we'll just quickly see an example of a possible use case of where blockchain can be used. This was actually my final year project, wherein we tried to improve land records or the practice of maintaining land records through Hyperledger Fabric blockchain. So what we essentially did is we got all the stakeholders on the blockchain network, all the stakeholders, as in the landowners, the municipality, the tehsildars, all the people responsible for maintaining records of all the land records, all the land acquisition records, ownership records. We got all of them on one Hyperledger Fabric network, and we made a system such that any edit made to any land record is always reflected in the blockchain. So the reason why this solution was appreciated a lot is because while there is digitization of land records in place, it's again based on the traditional client server architecture, or all the participants are not included. So what happens is, if for example I make an edit and the landowner does not even come to know about it, that is how most frauds in these cases happened. So that's why we decided to include the landowners as well as all the people in the bureaucratic chain pool to be included on one network. So we decided which documents are required for establishing land ownership, such as these. Next, um, next we decided which stakeholders to include, which participants to include in the network. They're called participants in the case of blockchain. And next, together with Hyperledger Fabric and IPFS, it's interplanetary file system. It's a decentralized system for managing files. That's something we'll cover later. And passports, we devised a solution for improving land acquisition and record management. Next is again the working of Hyperledger Fabric that we have covered. So we'll move on. This is how we defined our business logic, that the application SDK will be where the land record admin will be making new edits or new entries to the transactions, which will then go to the endorsing peer as discussed. The endorsing peer being the district and the city registrars, who will verify if the if the edit is valid or not. And the ordering nodes were proposed to be the state government office that will group all the valid transactions into blocks, and the committing peers for the city municipality offices that had to commit the blocks in the blockchain. Next, so um, Hyperledger Fabric is actually an open source solution provided by Linux in association with IBM Blockchain. And Hyperledger Composer is a proposed solution. It's actually not proposed anymore. It's a solution by IBM Blockchain, which provides an abstraction of sorts to Fabric. So the chain code in Fabric can be written in Golang, Google's very fast programming language, or Node.js. But that right, uh, but that requires the network manager to know how to code in Golang. So Composer here provides a nice abstraction. It defines the entire business logic through three parts. There is a participant, or there are multiple participants or stakeholders, as we saw: city, municipality, landowners, realty office, state government, etc., etc. For example, in this case, they're participants. There is a defined asset, which in this case is land, and together the participants can perform transactions with the assets. So that's how Hyperledger Composer provides a nice abstraction for Fabric, defining only three things: participants, assets, and transaction. Next. Here, we see that there are various components to a business logic archive. The first being model file. So, in the model file, you define all the participants, you define all the assets, and you define all the transactions that are involved in the network. In the script file, you write your transaction logic in simple JavaScript. In access control, you determine which participant has how much access, if they have read access, write access, or both. So in this case, obviously the landowner should have only read access. They should not be able to make edits, because well, then all of us will just end up owning more properties than we should. And all of that is then grouped in a business network archive, which can, to draw a rough analogy, be compared to a zip file. Now, that entire business network archive, along with a card file, goes to the Hyperledger Fabric cloud, or it can be stored in local. So if you're running in Apache web server, you would display the blockchain on the local host. So in that case, you put it on the local, or you can put in the Hyperledger Fabric cloud, for your network to be available across platforms and across networks, as in across Ethernet networks. And you can put it on the web browser, you can put it online, you can put it wherever. Next. So this is actually a screenshot of the backend. Unfortunately, I don't have my laptop right now. Otherwise, I would have loved to show you guys a demo of how the application actually worked. But we'll have to make do with the screenshots. So if you can see here, this is the back end of the application. So here, well, starting at the top, we have defined our asset as land title. We have defined our participant as a method called person. We have defined our transaction as a method called register property for sale. Now, for making any edits from the backend, like how any REST API works, you have to open the post section. You have to click on the try it out button, and there'll be a JSON string. You have to put in your relevant values, and then you have to send it to get 200 OK. And if the transaction is valid, you get 200 OK if the business logic is satisfied. Otherwise, you get any other, you get 500, that is internal server error, or you get you get verification error if there's not proper verification, or whatever. So that's how this works. Next. So this is the front end that we developed on Angular. So here, as you can see, there are three basic entities. There's a participant, there's an asset, and there are transactions. So in the asset section, the asset being land title, you see that the asset ID is defined as title ID. For example, Malad Thane Virar, and the owner is resource colon test dot person. Person is the participant, and hash and the number after it is the participant ID. So if you look at the first entry, it basically means that all right, I'll make this quick. So this is how each asset is mapped to each participant, and the document hash that you see is developed through IPFS. So here, what essentially happens is we posted all of the documents that were required for establishing land ownership on IPFS, and the document hash was generated through it later, which is something that we'll quickly see later. If we can move on, this is the transaction section. So if you can see behind, you need a seller and you need a title, and you need a buyer and transaction ID and timestamp for the transaction to be valid. But from the front end, you can put values of only the seller, the title, and the buyer, which means that the transaction ID and the timestamp is being put by the blockchain, which is something that you as a user cannot put on your own. So here, this pop-up basically shows that the seller is the participant with the participant ID 1. The asset is the asset ID Thane, and the buyer is the participant with the participant ID 2. So when I click confirm, the next what happens is, this is a screenshot of what happens in the backend. So if you can see, transaction ID and timestamp could not be put by me, by the administrator. It's put by the blockchain in itself, which shows that the transaction ID, if you look at the string, it's virtually impossible if you do the permutation and combination to generate this string on your own, or to try to modify this on your own, which is how we can define that Fabric has indestructible trust. Moving on. Well, this is a screenshot of IPFS, which is Interplanetary File System. So once you have the IPFS daemon installed, you select the file that you want to upload. So here in this case, through IPFS add test.pdf, I uploaded my test.pdf on the IPFS network, and I got an associated hash with it. So if you remember, in the asset section on the front end, we saw a document hash. This is basically what we put there. Now, but the catch here is that anybody who has this hash will be able to view your document. So obviously there are additional safeguards that you can put to ensure that this hash is not publicly available to everybody. But to get the document associated with the hash, you just have to do IPFS get and put the hash, and the file gets stored in your directory wherever you are. Currently, I was in home itself, so the file name though will be the hash and not the original file name. Okay, moving on. Well, with passports, we had OAuth, which is basically an integration with external services like GitHub or Twitter or Facebook or something, wherein we had this additional step of providing authentication and authorization. So this screenshot basically shows that even on the back end or the front end, without proper validation, you could not make any single edit. Um, yeah, that shows that authorization is required if you try to maliciously make any edit. Um, yeah, that's it. So, thank you so much, everybody. And I'm so sorry for taking so much of your time. I hope you're not late for your other lectures.